Welcome back to another dynamics example. This one I'm calling the other Newton's second law example from the February 1st class. We didn't get to this one either. This is a much harder example in my opinion, but it's got some features in it that I think will help you get the idea or the technique, the tricks to trying to do some of these problems. They're not that difficult, but you have to kind of approach them step by step and sometimes go past a little bit of struggle to be able to figure out what the idea behind them is. All right, so with these two blocks are going to slide down. This one's going to slide down the incline, and the other's going to slide down the other block. So there's going to be some relative motion going on. That's something that we could use as one of the keys to be on the lookout for. All right, so there's no friction in this problem. We're neglecting friction, which is good for us. It's going to take away some of the complexity. Says the relative motion is going to be enough complexity for us. So block A, its weight is the 22 kilograms times acceleration of gravity. Okay, so I've already done that right here, and I've already done that right here. Okay, so there was no reason to do that. All right, so let's see. It won't let me erase sometimes. There we go. All right, let's pretend that never happened. I could edit that out, but what's the use? So the first thing we're going to do as part of our technique is to make a free body diagram and an inertial diagram, the FBD and the IBD. And I'll do this, walk through this, and then I've written it out on the other page. The angles are going to be something of a roadblock for us, or a challenge. We'll get to that here in a second. So we start off with block A, and let's see, one of the easy things is we'll make the normal force of block A against the inclined surface. Now here is the normal force of block B that's exerted on block A. And that's sort of the gist of what makes this sort of complicated, is that B is exerting a force. Although it is sliding, it's also exerting a force downward onto A and encouraging A to accelerate down this slope. And to be very careful with the directions of angles here. We also have the weight of A acting downwards, and we have no friction. All right, so I could draw that in here, friction of A, and just make it go out. And we also would have some amount of friction resisting the motion of B. So wait, it should actually be in the other direction, right? If it was going to be on there. So, but I just want to point it out. Okay, so B would also be exerting a friction on here, because we want to do an FBD and an IBD. I'll do it over here of block B as well, and it would have a normal force NB as opposing, and its friction would be going resisting, right? FB would be resisting its motion, which would tend to be sliding downwards. It would be accelerating in this direction, motion of B times the acceleration. And I'm going to leave the subscript blank for right now, because we want to make sure that's going to be a key feature coming up here in a second. We have to think about that. So that's going to be the weight of B. And then we're going to take the acceleration of A. It's going to be entirely coming down the main incline. So that's the mass of A times the acceleration of A. And I forgot to make that 0, and I'll just try to remind myself that the friction is neglected, so it's off. The angle that we want to make for this is going to be part of the key of this problem. It's going to be aligned with the main incline, so that's going to be 30 degrees. Okay, here's where we're going to have to use a little bit of a trick here. Over here on the other free body diagram IBD for mass B, or block B, here is like what the horizontal and Y are, but we want to line this one with the incline of A, and that's going to be 20 degrees. This one I'm going to name X prime and Y prime. That's going to mean that this one right over here on block A is going to be, let's call this like the primary axis, and this is a secondary axis that we're going to make. Now, I left this subscript over here blank for A, for the acceleration. If you think about it, this is actually going to be acceleration of block B with respect to A, right? So let's write that, block B with respect to A. But it's also going to be sliding. It's going to be sliding down A, but it's also going to be sliding with A, right? So it's going to be going down. The slope of A, this same slope, is going to be going down. So that's going to be the mass of B, but it's going to be the acceleration of A. The way to think about this is that we could have drawn, instead of these two accelerations, just the acceleration of B. But the acceleration of B is equal to the acceleration of A plus the acceleration of B with respect to A. Okay? Now those things, instead of just applying the mass times the acceleration of B, we can take the mass times the acceleration of A and the mass times the acceleration of A with respect to B, that acceleration, and we can combine those. All right, so that's like the key right here, right? The two things that are joining these together are that the normal force is shared of B, and also that the acceleration of A influences what happens to B, and this is the relationship where they meet. Now that logic might not seem immediately apparent, but if you think it through carefully, you'd be able to see it. Now the rest of the challenges is due to angles, making sure that we try to get these correct. And amongst the things that will help us is to make a very good sketch. Now my sketch was made while I was talking, so I might not have done a very good job. So I made a very careful sketch right here previously, where I tried to keep all the angles straight. So one of the main angles that's going to be a little bit confusing is this one right here of B onto A, and trying to get straight what angle that is. And so when we want to try to assign how much of it is in the X and how much of it is in the Y direction here, we're going to have to be very careful there. And we also have to make sure that we resolve them correctly. We'll see in a minute that we'll be able to do that by just very careful notation. Okay, so let's say the sum of the forces in the X direction of, the X direction is going to be equal to mass times mass of A times the acceleration of A, and that's going to be, we're going to make positive downwards, down the slope. I think I did that wrong. I'm going to try to be consistent with what I've already written. I'm going to make that positive here because that's where I've shown it to be positive. And in that case, the weight is going to be, there's going to be a component of the weight that's going to be negative WA times the sine of 30 degrees. And we're also going to have a portion of the normal force right here, right, which is going to be in the horizontal direction. And that is going to be minus NB times the sine of 50 degrees. See, cool. and then of course the mass times the acceleration would be negative here, mass of A times the acceleration of A going down the slope. And of course it's not accelerating off of the face right here, so this is going to be the entirety of the acceleration. So I can write 215.8 negative times the sine of 30 degrees minus NB times the sine of 50 degrees is going to be equal to negative 22 acceleration of A. I can write that the NB right here, because that's going to be an unknown, it's going to be equal to 28.72 acceleration of A minus 140.9. And you can work that out. Now I'm going to come over here and I'm going to say that the something I probably should have done over on the other side. Maybe I'll write it down here, okay? I'm going to go ahead and break down, this is an important thing, the acceleration of B right here. Again, just like I did over on the previous page, this acceleration of B is going to be broken down to the acceleration of A and acceleration of B with respect to A. But now I'm going to be careful here and break this down into components. There's going to be y prime and x prime. All right, so it's going to be in this coordinate system right here, that x prime and the y prime. And that acceleration, of course, is right here is the horizontal, turn from the horizontal, but then we know that the acceleration of A is going down the slope, so there's a total of 50. Right here, that angle is going to be 50 degrees right in there. And we also have that this acceleration, okay, this acceleration is going to be entirely in the x prime direction. So the acceleration of B in the x direction, x prime direction, is going to be negative A, acceleration of A, times the cosine of 50 degrees, right? We can see that right here. That's going to be this element of it. And I think I want to say that I should be making that, yeah, it's going to be negative. Okay. And it's also going to be the entirety of B with respect to A. There's no longer vectors because we're breaking down into components, right? So, and that's all positive in the x prime direction. And the acceleration of B, component in the y prime direction, is just going to be also negative because it's downwards in the y prime direction. And that's going to be the acceleration of A times the sine of 50 degrees, okay? So when we get back over to here, that's why I wanted to do it back over here. When we start using the FBD and IBD of block B, we could say that the sum of the forces in the y prime direction is going to be the mass of B, and it's going to be times the acceleration of B in the y prime direction, right? So it's going to be this guy down here, and that's going to be in, I keep drawing this wrong. Oops. So let me fix that. It's early in the morning, so that's my excuse. So okay, this is going to be the y prime, so it's going to be aligned with this right here. So I'll try to make that look kind of close, that arrow. And so we're going to have, this right here is going to be 20 degrees. So of course that's 20 degrees. So that's going to be the cosine, right? So the weight of B times the cosine of 20 degrees plus all of the normal force of B going upwards and there's no other forces in that direction. And that's going to be equal to negative, because that's the component right here. It's going to be the y component of this, so something along those lines right there, times the mass of B times, of course, this right here is where the negative comes from, the acceleration of A times the sine of 50 degrees. Okay. So just thinking about it, that's the acceleration of A, once again, is going to be affecting the normal force of B, right? So we could solve, let's see, we could stick some numbers in here. It's 98.1 times the cosine of 20 degrees plus what we got right from over here, that's NB, so we can go 28.72 times acceleration of A minus 140.9, and we're running out of room, so I'm going to go ahead and do a shift over here. Negative 10 times the acceleration of A, okay, times the sine of 50 degrees, okay? And look, we have A's, and we can solve for the acceleration of A. Of course, this is just the magnitude of the acceleration of A, right? Because we broke it down over here, so we were able to just use the magnitude of the acceleration of A. 6.406 meters per second squared. And we could turn this into a vector by giving it a direction. Well, we already know what the direction of the acceleration of A is going to be, right? It's just going to be down the slope at 30 degrees. So it behooves us to break this down into x and y coordinates in terms of the a global x and y. All right, so the what we normally think of x and y right here in the I and j unit vectors. If we do that, taking appropriate directions based on what quadrant this is in, we'll find this negative 5.547 I plus negative 3.203 J meters per second squared, because we'll always include the units. Okay, we're not done. That's the acceleration of A. We were asked for the acceleration of B. It's a little more difficult. Well, no, it's not really that difficult. We're just going to go ahead and pretend like we still have the other diagram up there, and have the sum of the forces in the x prime direction is equal to mass times the acceleration of B in the x prime direction. Okay? And if we did that, we would find, let's see, I'll do a quick repeat of what we had over on the previous page. We have some amount of continuity here. Let's see, here's the global, and here is the prime, x prime, y prime, and we have the weight coming down here, the weight of B, and the normal force of B, and that's all we have, right? So here's their 20 degrees here, and remember that we had acceleration. See, so this is mass of B times the acceleration of B with respect to A, and then we had, coming down here, had the mass of B times the acceleration of A, and I think we have it all done. Remember that this right here we figured out was 50 degrees. All right, so we take in the there's going to be this for us, it's going to be a positive WB, the weight, times the sine of 20 degrees, right? So that being the positive x prime direction, and there's no other forces acting on to B. So then we're going to have the mass of B times the acceleration of B in the x prime direction. We had previously found that to be, and breaking the thing down, as being acceleration, I think it was negative a times the cosine of 50 degrees plus the acceleration of b with respect to a. Okay, so it was the entirety of that. We could also have done it by looking at this. So that's going to be negative times the mass of b. I should have drawn b up here, by the way. Oops. Times the acceleration of a times the cosine of 50 degrees plus the mass of b times the acceleration of b with respect to a. Sticking some numbers in here, we have 98.1 times the sine of 20 degrees is equal to negative 10 times the acceleration of a, which we found, of course, this is just the magnitude, right? So it's the magnitude that we found previously of 6.406 times the cosine of 50 degrees plus 10 times the acceleration of b with respect to a. So now we're going to be able to find the acceleration of b acceleration of b with respect to a. There you go. And of course, this is also the magnitude, right? So if we do that, we found it 7.473 meters per second squared. And noting that this acceleration of b with respect to a is just going to be 20 degrees down below horizontal. So we can go ahead and write that out right here and make it a vector. Should have gone that way. Okay. And we could break this down into components as well, into global x and y components. And doing so, we would get 7.022 I plus negative 2.556 j meters per second squared. And now we could find the acceleration of b is equal to the acceleration of a plus the acceleration of b with respect to a. And doing so, we would find that acceleration of b is equal to negative 5.547 plus the component in the x direction of acceleration of b with respect to a of 7.022. That's going to be I plus negative 3.203. Whoops. Minus 2.556 j. And so the acceleration of b is going to be equal to 1.475 I plus negative 5.759 j. That's meters per second squared. We could also write the acceleration of b is equal to, we can find what the magnitude is of this. It ends up being 5.945. That's just taking the square root of the sum of the squares. And that's going to be, and then we'll take the tangent of this over this, and we'll find that it's going to be 75.6 degrees. So there's the answer to part A of this. Part B is simply asking for the velocity of b relative to a at half a second. Well, we can just do that as a linear, a straight line, and kinematic constant acceleration problem. So the velocity of b with respect to a is going to be equal to velocity of b with respect to a originally plus the acceleration of b with respect to a times the time. So trying to squeeze this in, velocity is going to be equal to, of course, 0 is starts at rest times our where did we go here? This acceleration, so it's 7.473 times our 0.5 seconds, and we're going to be equal 3.74 meters per second. Now, we're not done with the problem. Let's see if I have another page here, because I can't squeeze it down here at the bottom. we need to write this out as velocity, right? Because it's a vector. So it's our answer, 3.74. I'll just use 3 sig figs like we're supposed to. And we know that it is going down the slope that's 20 degrees. So that's what the velocity is, a velocity of b with respect to a. Like I said, there's a much, well, not a much, but it is a harder problem than the original or the other example. And I want to caution you against being overwhelmed by the complexity of a problem like this. Instead, pay attention to the steps, pay attention to the logic, and some of the big picture. Once again, the big picture is that B exerts a force against A, and we don't know what that force is. So that becomes sort of the key, is to find that connection, that interconnection between them. So if we just go through the methodology and start looking at A, we might have started with B, right? We might not have known where we were going, so we would start with B and start looking and setting the thing up. And maybe we would have gotten, let's say, was started with the Y, because we knew that we had to get that normal force, and we got maybe this far right here, right? Maybe we would have started there and gotten that far and said, oh, look, I need the acceleration of A to be able to find the acceleration of B. Okay? And in doing so, we would have had probably had the acceleration of B instead, and said, oh, I don't know what the acceleration of B is. I don't even know what the direction is, so I might have been stuck right there. So the next thing we would have maybe recognized is that we have a relative acceleration problem. And then we could have broken it down. All right. I would consider this sort of the trick of the problem, and sometimes it's not that easy to see the trick, but breaking it down or breaking down the concepts and thinking and using those as sort of like investigative tools is sort of the key to overcoming some of those tricks and trying to find them. I hope this helped, and I recognize how complex this problem ended up being. I hope that doesn't discourage you from attempting the problems and gaining that insight and breaking through those barriers, or trying to figure out what the trick, quote unquote, trick is behind the problem. All right, so thank you very much, and hopefully I'll see you in a new video soon.